Refreshing.
Okay, it's live now. So that sounds good.
Yeah, just checking. So, yep, we're live.
All right. Hello, everyone. Welcome to Quadcast. I am your host, Tim.
Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So, without further ado, let's get to it. Um, So Tim and Mikey, I thought last week's episode on Microsoft's alleged quantum computing claims was really interesting, and as per requests from our viewers and listeners, they're very interested in a continuation of this episode, more delving into the physics of quantum computers and also the physics of what Microsoft is trying to do. And so I wanted to first, I guess, maybe summarize the previous episode, like the tidbits of like how this came into the mainstream news, and then we can delve into the physics. So I guess, Mikey, I'm just to throw this on to you. You look really eager.
Oh, actually, I'm eager to backtrack and start even earlier than that.
Go
Because
for it.
because I don't want the viewers to get the impression that anyone has any idea of what they're doing right now, because that's not true at all. Like literally,
Hmm.
what we know, all we know is that if we can make a computer out of parts that obey quantum logic, then some magic can happen. And people have a lot of really bad ideas for how to implement this. And there are some ideas that seem good, but like most things, like you can't know if it's a good idea until after the fact. This is like we're really in the very starting phases of almost like explorative research in terms of like what's the best practices for doing this thing. So um, it's really like an open question, like how can you use particles as your components for making a computer? There's so many different possibilities for how to answer this. And as usual, bad ideas are way easier, more common to come by than good ideas. And so I guess the point of today is to describe what might even smell like a slightly more sophisticated idea than the totally stupid ideas that everyone is pretty much going down.
I mean, I think
Well,
I would go a little beyond that, right? Like we have
Beyond that, that
the,
was pretty harsh.
but
Okay.
you know, because the field is still early, but we have some theoretical ideas, and hence the title of this episode. There are a lot of people who believe what might be the most ultimate quantum computer given the current knowledge right now. And I would say Microsoft is trying to tackle that, at least from a theoretical viewpoint. Like they are trying to build the ultimate quantum computer, and this may look very different from what Google, IBM are doing,
Yeah.
but
Yeah.
they are
Wait.
giving us that.
Yeah. Can I just say one thing that I wish I said last week? If you look at like what Google, IBM, and Rigetti are doing, they're basically taking like typical hardware architectures that we know right now, and they're trying to kind of like apply them to quantum computing. They're trying to make like a quantum version of like current CPUs, which is really stupid. If you think about it, it's like kind of like trying to design an airplane and designing it after like bird flapping its wings. Like that would be so difficult, right? There's like that is not going to be the best way. Like the best way to make a flying device is not to copy birds because those mechanics have evolved over thousands and thousands of years. There's probably an easier, quicker way to do it. Um, and so I don't know. I feel like that analogy is pretty apt for a lot of the architectures that some of these startups and big tech companies are chasing right now.
yeah, that's a great summary. And I want to take a step back and touch upon something you mentioned, Mikey, which is you mentioned like they're really, really dumb architectures.
Yeah.
and really like maybe not so dumb architectures. Who knows if it's like the smartest architecture?
Yeah.
As we're discussing this in the context of building up to what's the ultimate quantum computer, can you talk about the more naive, maybe like things you think are going to work slash dumb or whatever, insert whatever word choice you want to use?
Yeah, no, like I think that the dumbest thing to do when you're trying to get to the next level. Well, okay, sorry. I mean, I use the word dumb like not in a bad way. Like so, one like the top physicist Nima Hamed has a thing he always says. He's like, if you're trying to solve a problem, there's like an algorithm for solving a problem. First, you try the dumbest thing you can think of. If that doesn't work, you try the second dumbest thing you can think of, and you just keep the third dumbest thing, and you just keep doing that until you solve the problem. And that's coming from one of the greatest geniuses that mankind has seen thus far in recorded history, at least. So, like, I use the word dumb with all due respect, but I would say naive. Like the naive thing to do if you're trying to fly is to look at birds and try to develop some kind of flapping device because
Mhm.
it copies your everyday experience. So I guess the naive thing to do with quantum computers is to take these uh, like transistor wires that we use that we've perfected. We've gotten exquisitely good at making tiny, high functioning, efficient transistor wires to hold computational information. And so we could just imagine making a superconducting version of that, which would allow quantum effects to become more apparent and just basically, but everyone knows that current modern computers, the designs are ridiculous. They're steeped in historical accidents, steeped with inefficiencies due to these historical accidents. Like there needs to be some like back to the drawing board type thing here.
Yeah, well,
And yeah,
let me just add a few words on how these typical superconducting qubits work. Basically, yeah, like Mikey said, they take these wires, they make them into superconducting state. What happens when you have superconducting state is that electrons, they pair up, form what we call Cooper pairs. Like pairs of electrons come down, bind together. And what's interesting is that when they combine, they form what we call bosons. And we'll talk about why bosons are a big deal or not. When bosons happen, their quantum mechanical property get amplified. Like the whole wire now becomes a quantum mechanical object. They exhibit quantum mechanical behavior to the whole wire, basically. So now, like you said, it becomes a quantum mechanical version of a wire. Now you can manipulate it by pretending that it has different quantum mechanical states. It can be in linear combinations of different possibilities, and then you do computing that way. I think that's the basic superconducting quantum qubits, and that's what Google's doing. IBM, I think, probably a few
roughly.
others.
I'm sure they have their own spins and
Right.
creative, but basically that's what it is, right?
Yeah.
Yeah, yeah. And we've talked about these superconducting wires, which is some version of that Google and IBM are doing. What is, I guess I'll just ask the question of this episode, like, what is the ultimate quantum computer? Does it have anything to do with the recent press of, what Microsoft has announced? I know we don't want to attribute it to Microsoft, but it's through their press announcement that this has become more I guess like widespread in terms of people knowing certain terms and whatnot. So I guess Tim, I'm going to point this question to you.
Okay to attribute it to Microsoft because they invested, like they really made the big investment to chase this, and so I feel like they do kind of claim this, right? So I don't know what word should we call this thing. Last week we were debating on whether we should call it Majorana computing or anionic computing.
Yeah, I
I
think if you go
think.
if you
Oh, go
use
ahead, Tim.
if you try to compare this to the Bose-Einstein condensate, which is Cooper pairs in superconducting qubits, these are bosons. They use bosons, right?
Okay. So
If you,
wait. So would you say that like typical IBM style quantum computing would be called like bosonic quantum computing?
yeah, I think so.
Okay.
I think that's fair. I think that's fair.
Okay.
So
Good.
so
Good.
I
Good.
would
We got to give it a better name because superconducting quantum computing is not an informative name. We should call it bosonic quantum computing.
yeah, but yeah. But I would say that the what Microsoft's trying to do is categorically different, completely different. So instead of relying on bosonic bits, these fundamental units of
Wait, hold on.
computing.
Sorry, I don't want to cut you off to continue, but like, would you say that trapped ions is kind of like fermionic?
I'm not familiar with that,
Oh,
so I
I know.
can't say.
I'm pretty sure it is fermionic. I think
Sure,
you can distinguish like between fermionic and bosonic quantum computing.
sure,
That's
fair.
cool. And photonic quantum computing is obviously bosonic quantum computing.
Yes, yes.
So that's cool. So this
Yeah.
is categorically different, as Tim was saying. Sorry, continue.
Yeah, so it's categorically different, but and I think there's a theoretical framework on this, and it's probably fair to say these are what we call anionic quantum computing.
Yeah.
And
Not boson, not fermion, but any. That's a joke.
I appreciated it. I go ahead, Tim.
well, I mean, Mikey, you can explain. I think you know a little bit
Well,
more.
no, Frank Wilczek is a fun. No. I'm just saying, pointing out Frank Wilczek is a funny man. No. Like, continue your train of thought, and then I'll.
Yeah. So what that does is last time we described this. So in particle physics, fundamentally we have two kinds of particles: fermions and bosons. And the difference is that it's basically a sign difference, plus or minus one. And there's this funny thing called the boson or fermionic statistics, is that when you flip two particles, let's say you have two particles, you spin it around, 180 degree, you exchange them. You either pick up a positive sign or negative sign, and that's just reality. We're stuck with that, right?
I guess Tim, can you explain like I guess a more I guess like a little bit less abstract of like a difference between bosons and fermions and more of like in everyday life, like why are bosons important versus fermions? Like why is that distinction important?
I don't know if this is what you're alluding to, but I watched last week's episode back, and I realized you were alluding to something, and I missed out on that.
Oh, I mean, I could allude to it right now.
Yeah, but like,
Yeah.
well, yeah, okay, yeah, well, but I feel like the description of it, it's exactly related to what we're talking about, but I
Mm.
just didn't. I didn't see the connection at the time, so I'm worried like it might not be obvious to the audience what the connection is. So
Yeah, I mean,
like
I just want to.
maybe. Oh, sorry.
No, go. What were you saying?
Oh, I thought maybe Tim could explain what he was going to say, and then I could follow up to clear up the thing that I was wrong about that you were right about last week.
Oh, okay, yeah, go for it. Okay, go ahead, Tim.
Yeah, I think it'd be yes. So Tim.
Yeah. So what you can argue is quantum computers. You're in the business of measuring something called phases. It's a measurement. You can measure, let's say, right? And the whole goal is you move particles around, you measure these phases.
The phase is the thing that stores the information.
Yes.
Right. It's like it stores your answer to your computation, basically, and then you try to manipulate this phase, and then like basically like if 1 + 1 is 2, like the answer 2 has to be encoded somewhere in this thing we're calling the phase.
Yeah. So in a quantum computer, let's say you have 2 qubits and you just swap the position. And then you measure it and see how that's changed compared to the original. In nature, there's only 2 possibilities, plus or minus 1. Positive or negative. It just has to do with the way the world works. It seems like it's impossible to get around that fact.
Well, no. Well, let's be clear here. So if I have 2 identical particles and I switch them, you would think that there would be no change. So no change is multiplication by +1. If I multiply a number by +1, that does nothing. So intuitively, I would think that if I take 2 particles and I switch them, and if they are identical, if they are literally identical, like provably identical, I would think that if I switch them, this is like multiplication by +1, i.e. does nothing, right? That's what I would assume would happen if these particles are identical. Continue.
Yeah, well, I guess, there's a small loophole because in quantum physics,
yes,
yeah, we don't just measure the we measure the absolute value, so the sign doesn't matter as much.
We measure quantity squared, yeah.
Yeah, so that's why the loophole is that therefore it can be plus or minus 1. Like the negative one, in some sense, immaterial. But but technicality aside, but if you just have plus or minus ones, it's not very helpful for computing. I mean, that's
Yeah.
what it is. Like you just
Well,
have
you just can't you can't store that much information in just 2 bits. I
yeah.
mean, well, that's what we do now, but we need lots of them. But it it's sufficient, but it's not ideal. So,
Yeah, but what you could get around it by doing like what like swapping particles as a computational tool is not viable because like we said when we swap particles we just pick up plus or minus one.
normally you would think that that's not good enough. Normally you would think if all I could do is swap particles, normally you would think that's not good enough to compute anything.
Yeah,
But wait, can I just rectify my mistake last week right now? I think this is the appropriate time. Hold on to the thought.
sure, yeah.
Okay.
Yeah. So last week Sahil was talking about like how like particle. So actually, this like Sahil was saying was absolutely correct. Like this is absolutely like so. The main difference. So Tim was mentioning there's two types of particles. There's fermions and bosons. There's particles that are identical in such a way that they're unchanged, meaning times plus one when you switch them. And there's particles called fermions that are identical in such a way that when you switch them, you pick up a minus one. But as Tim mentioned, um, because the physical properties only care about the square of this quantity, this minus one doesn't matter. So we still consider these things to be identical. And one property of that is, and this is the main difference between bosons and fermions, that bosons can occupy the same space. Like literally you can pile an infinite number of them in the same physical location, the same point-wise physical location. Fermions, you cannot. There's a limit to how close you can put fermions together, which is around equal to the Planck length. And that's the reason why neutron stars have the size that they do. Anyways, that's irrelevant, but and the reason for that is, as exactly as Sahil pointed out, is because of this fact that if I switch them, I pick up a minus sign, which means that the only number that's negative of itself is zero. So this
I
is
don't
the
know if
reason
people are gonna
why.
fully follow that because like that was from last episode. Maybe
I
you could
know.
explain.
I
Yeah.
just needed to rectify. But can we put a link back? Like if they like, just go back to the last episode, please, and go to like I don't know, like minute 8 or something. Like, but like it's a really deep fact about bosons and fermions that like really ferments or cements the picture in terms of what the physical distinction between these particles are. So to find
I,
that there's like a third category is super surprising and crazy.
I mean, a really simple example I would give, just kind of, maybe there are more subtleties, is that when I shine a beam of light, it's not like the light needs to keep increasing in energy as more photons come out. They can all be at the same low
Yeah,
energy
because
state.
photons are
Ver-
bosons, so they can just pile up on
yeah,
top of each other. Yeah,
yeah.
exactly.
Versus like the periodic table when you have like a lot of electrons, they go on outer shells and they go
Yeah,
further out, and it gives rise to essentially chemistry. If fermions behave the same as bosons, you'd have no chemistry as we have
oh,
today. So
yeah,
that's
we
that's like that's an
radically different. Yeah,
example that I give.
yeah.
Yeah, anyway, so okay, we've cleared up the distinction between fermions, bosons. There's this third state, which doesn't really, as far as I know, it doesn't really occur like quote unquote
Wait,
naturally
no, I
per
cut
se.
off
This
Tim
is
before he could. I cut off Tim before he
oh
could go on with that.
oh go ahead, Tim. Sorry.
My bad.
Oh yeah, well, I mean, it doesn't occur naturally in our universes, but it turns out that if you create kind of like a fake, like an emulated universe, it could
Yeah,
happen. And
yeah,
that loophole only happens in 2 dimension. So it turns out that a material is kind of a toy universe. If you just have the right kind of material with like a lattice structure and electrons in there, and it's large enough so that you kind of squint real hard a little bit, it is possible to engineer, like imagine like a really thin slab of some composite material of different arrangement of atoms. You could create a toy universes where you get this exceptional exceptions where you don't just have plus or minus one. You get something in between. And you can actually engineer how much in between that is by playing with the material. And that's sort of the crux of the quantum computing, using anyons.
Yeah, it's
I
really
want
crazy
to.
if you think about it, right? So the first thing to make clear is that so we live in a three-dimensional universe, three spatial dimensions. Um, in a laboratory, we can simulate a universe with two physical dimensions. We can literally simulate this like almost exactly. Not perfectly exactly, but like almost exactly. We can simulate we can't simulate a universe that has four physical dimensions because that's beyond us. But what we can do is we can just you know like on a board game. If we play a board game, we're simulating a two-dimensional universe, right? There's only two directions of motion. In a laboratory, we can create materials where things can only move in one or two directions, and so we're essentially simulating a two-dimensional universe. And so for the longest time, it was just assumed that there could only be two types of particles, bosons and fermions. There's so many reasons to think that the distinction should be discrete. But in 1983 or something like that, one of the great geniuses of our time, Frank Wilczek, was just sitting around, I don't know, in his house, I guess, just musing about things as he does, and realize that if you look at a two-dimensional universe, then you can actually, there's a loophole, as Tim mentioned, that you don't need to have just bosons and fermions. You can have any continuum of particles in between. And then later, like 20 years later, the magnanimous Alexei Kitaev realized that if you could use such particles to make a quantum computer, this would almost be like the ultimate quantum computer because it would naturally have error correcting properties.
Mhm. I want to take a stab at maybe and then see what you guys think of explaining why two dimensions is so unique. Like, why not three? Why not one? Why two specifically? My understanding is that.
Why two is unique is hard. Yeah. Sorry,
Oh,
continue.
let me take a stab at it. This is an
Yeah.
explanation I heard, so don't shoot the messenger.
Yeah.
But what it is like, in three dimensions, if I take two particles and let's suppose I have a plane and I exchange them clockwise or counterclockwise in a plane, I could simply rotate that plane by 180 degrees and I could transform a clockwise rotation into a counterclockwise rotation.
Yeah.
But in two dimensions,
The
I
mirror
can't do
universe.
that. Yeah,
Yeah.
in two dimensions, I can't do that. So I can distinguish between clockwise and counterclockwise. So that's an explanation I heard of why anyons exist in two dimensions, but can't really exist in
Yeah.
three dimensions
I,
or higher.
I think that's a fair explanation. The really the crux of this is obstruction. Imagine if we live in a two-dimensional world. If Sahil, you're in my way, like you are stuck. Like imagine you play like Mario, right? Like you have these blocks in front of you. You gotta jump over it. But in 3D, I can just whoopsies. I can just go to the side. Like how big is that wall? So in 2D, you have these obstructions, and because of these obstructions, you can wind around. You have these complicated paths, and the system can remember that. Like the obstruction. Obstruction is the king of creating these complicated structure, and because of these,
is that the curse of dimensionality? So are you saying that like in higher dimensions, there's too many ways to go around?
yes.
So you can't stop me. You can't stop me from getting around.
Yeah, exactly. So and this has to do with topology. For example, like imagine I tie a knot right now. I tie a knot, and a knot is a sensible object in 3D. But if I go to 4D, you can prove that any knot that I can tie, I can just unwind it in the extra dimension. So this is sort of like that. Imagine if I wind a loop around like a little hole, If I have an extra dimension, like Sahil, you said, you can just flip it over and that loop is gone, But in two dimension, if I have a thin material, well, the electrons can't go out of the material. So it's kind of stuck. So I have this artificial universe where like it doesn't have a way to leave the material. And therefore I create these obstructions. Obstructions are great because it adds complexity to the system and it allows more computational capacity. It just gives you more to work with.
Mhm.
Okay, sorry.
I want to.
I studied this loosely, but I said okay. But I just want to. I think I learned something new from this discussion. What you're saying is that like basically anionic quantum computing, like by restricting the dimensionality of my computer, I'm making it easier to keep track of my history, which makes it easier to correct for errors.
Yeah, yeah, I guess. Yeah, I guess the crucial point is like we want error resilience. You know, like
Yeah.
Mhm.
imagine I loop around, and if I do it on a computer, like simulate a looping around, I don't know, like there could be errors. Maybe a bit got flipped, whatever, and the loop is gone. You know, but if I do it in
Mhm.
this restricted material, literally it can't. Like how does it unwind? It has to retrace a step to go all the way back, and that's like really unlikely. You know, you got
Mhm.
like some cosmic ray has to destroy the material or whatever for that to happen. So you get this resilience because like you're looping around, looping, and then that gives you a basis to do computation, and that's totally different from how normally you can do computation.
Yeah, I would assume one dimension would be far too restrictive.
Yeah, no, so I was going to say, yeah, so there's like this balance, right? Like, so with higher dimensions, you have less restrictiveness, so you can do
Mhm.
more, but then such also introduces the possibility for errors that you can't track. If you go to lower, like, so one of the big differences between topology and dimensions is like in 2 dimensions, if I want to look at like a bounded area, the simplest way to do that is a circle, right? And the bounded area is a continuous region. But if I drop down to 1 dimension, then my bounded region becomes just 2 points, two endpoints, right?
Mhm.
Demarcating like the start and the end of it. So when I go from 2 dimensions to 1 dimensions, boundaries go from being continuous to discrete, like discrete points. And that yeah, like as exactly as you pointed out, that that inhibits your ability to encode information. So I guess it's kind of like a Goldilocks zone in terms of like what dimension is kind of ideal for doing having the flexibility to do computations, but also not being so flexible that errors are impossible to track.
Uh, Actually, this kind of gives rise to. So I just want to ask a really speculative question. If we lived more like we were able to perceive slash like lived in more than like three dimensions, say five, six, 10 dimensions. I mean, ignoring string theory and all, would it just be very noisy? Like, would nothing be able to like do anything? Would there be so much error? Or
If they
just
were large,
curious.
if they were large dimensions, it would certainly be difficult to keep track of things. Yeah, but I mean, but in
Yeah.
string theory, the extra dimensions are curled up, so
No,
there is
I'm talking about
a way to localize.
large macroscopic.
I think there's a reason why the number of dimensions we observe is sort of at the minimum of what's required for interesting things to happen. You can have very interesting things happen in higher dimensions, but like I think you have to point out, it's almost like too chaotic. I mean, I'm just
I
playing God
see.
here. I'm not actually God, but I'm just like
Yeah,
hypothesizing what God might think if he was
yeah. I think
conflicted.
one of the problem with higher dimension is that things will get too spread out. Like for
Yeah.
example,
Mm,
sound
It's
waves
the
will
curse
get
of dimensionality. Like things get
yeah.
nuts. Yeah.
Sound waves will get really spread out. So I don't know. You might not be able to hear your
Dispersion
neighbor.
becomes exponential, right?
Yeah.
that's
Uh,
fair. That's fair.
we
Yeah.
like it's very important that the number of dimensions we have is very close to the minimum of what's required.
Yeah. 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 So I want to get to a few audience questions that were asked. How is this new state that Microsoft did different than a Bose-Einstein condensate?
Oh, it's
Maybe
very
you can also
different.
explain
I mean, okay,
what those two things are.
it's similar in the sense that they're both like very drastically like radically different phases of matter than anyone could have expected. But from a physics perspective, their properties are almost as opposite as
Yeah. So
you can
let me
imagine.
let me just add that probably even what Microsoft is doing do require a Bose-Einstein condensate because
Yeah.
we need a superconducting material to even build this. But the typical superconducting qubits, it's just a superconducting wire. There's not much more to it. Of course, there's also a lot of engineering and whatnot. But for these anionic states, it's more than just a superconducting state. You need the superconducting state where you get Cooper pairs, but you need something more. You need obstructions, and we can talk about this later. And that comes in the form of magnetic field, which form vortices in the material. And so it's more than just a Bose-Einstein condensate. Of course, it probably needs Bose-Einstein condensate, but it's Bose-Einstein condensate plus something more. And usually people categorize it as a topological material. So it's not just some Josephson junction, not just some superconducting wire.
Yeah.
It's more than that. It's much more than that.
Yeah. So so you almost say like so, but I think they're similar in the sense that like a Bose-Einstein condensate leg. So once people started understanding quantum mechanics, people started doing calculations and started realizing, oh, there could be something like a Bose-Einstein condensate. Just theoretically, there'd been no experimental evidence for it, but the theory said that such a thing should exist, which just had crazy properties that seemed completely seemed completely crazy. But the theory said it should happen, so they checked, and lo and behold, Bose-Einstein condensates do exist. This is a similar situation where people are doing calculations saying that something like an anion should exist. In order to make one, as Tim mentioned, you would need to first make a Bose-Einstein condensate, but luckily we already know that exists. It's a really, I think it's just a really like triumph of human imagination that these materials that only exist in our heads twice removed, could actually exist, and people are actually chasing it.
Yeah, that makes sense. I'm curious now. So delving into it, like, can we sort of, I guess, give more intuition around why this thing Microsoft has proposed of doing is more error resistant? Like, why is it so special? Like from a physics standpoint, what is the big deal about this?
Okay, so I have to leave a little early, but I was really proud of the analogy that came up last week, but I realized I didn't describe it properly. But just okay, so imagine that like you're walking along some street and someone has a table where they have 3 cups and like I don't know, like some like a dice or something. Everyone's seen this, right? So there's this trick where they put an object under a cup and they have 3 cups and they rearrange them over and over and over again. And then your job is to figure out which cup is the object under. And usually they're really, 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 really fast, and sleight of hand will typically statistically lead you to guess wrong. And so that's how they make money. So yeah, before I go, I just wanted to say, imagine that at the beginning of this exercise, there were infinitely flexible strings tying each cup to the ground. So every single time he rearranged the cups, like these strings would get braided around each other. If such was the situation, it would be very easy for you to just follow the strings and trace back which object the cup was under, hence correcting any errors. That's my closing piece here.
I guess, Tim, do you want to add anything to that, or?
Yeah.
I'll say goodbye right now. Thank you, everybody.
Okay.
Bye.
Okay.
All right, later.
All right. See you, Mikey.
See ya.
Yeah, I would say this and this lies into the field of topological quantum computing. Like this braiding idea is interesting. It's almost like the digital analog of quantum computing. It's kind of funny. Like why is digital computing so reliable? Because it's only zeros and ones. You can't go somewhere in between, right? But then the problem with quantum computing is that we harness the exponential power because if you have 10 qubits, because quantum physics tells you that all the possibility in between are realized, you basically get 2 to the 10, in terms of power of computation. But however, we discussed previously that quantum computer is kind of like an analog computer. You dial knobs or whatever, the possibility mixes a little bit here and there. So the analog computer is error prone. That's why we move away from it. We go to digital computing. Now this braiding, it's kind of like the digital revolution of quantum computing, basically. So how can you digitize quantum computing, but still have the exponential benefit, right? And the braiding, this is it. If you have the quantum mechanical version of the braiding, when you move one particle around another, each operation, it's discrete. You either did it or you didn't, right? The error in that is very, very small. Like the chance of you accidentally flipping particles 360-degree around, it's diminishingly small, right? So it's much, and that's the reason why it's so much less error prone.
One question I have, I guess maybe if you could relate the current not this anionic computing, but the way like Google and IBM are doing it, but like to analog. So my question is that computers have, as we discussed, bits that can be ones and zeros,
Mm-hmm.
and similarly qubits, quantum bits, the quantum analog of a bit can either be in a 0 or 1 state, but it's not like it can be like in 0.5 or like 0 or 1 or anything like that. It's like two discrete states. So when you talk about this continuum, can you elaborate further on that?
No. I mean, this continuum is apt because of thermal noises.
Mhm.
Even though you design, let's say what Google is doing, right? Let's say you
Sure.
design a circuit, and theoretically, the qubit can only be some quantum analog of ones and zeros, or half. Let's
Mhm.
say 1, 0, and a half, right? But the thermal noise could move you to half to 0.49. And that's just one noise. And multiple noise acting together could sway you. Maybe one, you get a little bit of noise. It goes from 0.5 to 0.4, and then to 0.3 to 0.2 to 0.1 to 0.0. And lo and behold, you've messed it all up, right?
Wait, real quick, what is this like point five, 0.2, 0.1? Because the state of like the
Mhm.
system itself, if you take a single qubit, is either 0 or 1. There is like no in between. If I measure it, I'm going to get 0 or 1.
Right.
So what is this? Yeah, what is this continuum that you're referring to?
Right, but the continuum is the possibility, right?
Mhm.
Because of course, when you measure a quantum mechanical thing, you only
Mhm.
get probabilities. Like maybe my qubit is 95% ones and 5% zero. Yeah. When you
Mhm.
measure it, sure, you get ones or zeros, right? But
Mhm.
that probability can tweak by a little bit at a time. The
Mhm.
noise can drive up or down this uncertainty. Maybe instead of 95%, now you get 90% because of your noise. Yeah. And
Mhm. Mhm.
maybe it drive it down to 50%. Who knows? And then all of a sudden your quantum computation is ruined. But for the anyons, it's different. You don't measure it. The measurements are quite a bit more robust because it's not like you are measuring the state. You're measuring how many times it winds over a wire. Yeah. So
Mhm.
even though your possibility might be a little off, but the certainty at which you say how many times it winds around, like imagine this. Imagine I wrap a rope, around a pole. You know, I
Mhm.
can measure where the ends of the strings are, and
Mhm.
certainly because of noise, I might do a really sloppy job the way I wrap my rope around the pole. The measurement could
Mhm.
be different. Maybe the rope is to the left, slightly to the left, slightly to the right. But the fact that I wind the rope around the pole once, that fact is independent of how sloppy the other measurements are. So basically, you're fishing out like a concrete number from a sloppy result. So that's what the anionic computing affords you. Like some of the measurement might be noisy, but the fact that you wind particles together, that those numbers are discrete. They're the digital analog of in quantum computing.
Mm. So actually, this pertains to an audience question that just came in, which is, wouldn't this be better stated as giving quantum computers the reliability of digital instead of making the quantum computer digital? After all, quantum computer still does not have discrete value.
I mean, in some sense, it is the winding is discrete. You know
Mhm.
you you can, and Google's announcement is a device that's able to measure this discrete value. Okay, but the devil
Mhm.
is in the details. The discreteness, it by itself is not enough for quantum computing. You need a little bit
Mhm.
more. You need some analog fact in it. So the truth is, the discrete nature of this measurement is robust, but to do true
Mhm.
quantum computing, because you can't create all the universal gates, basically, you have to add a little bit of conventional quantum computing into it. But
Mhm.
nevertheless, you have some portion of a quantum computer that is discrete and that's robust, much more robust anyway. So it is that the results are
Mhm.
literally legitimately discrete. You know, when
Mhm.
let's say your computer, imagine you're able to build it, you can have a bunch of these anion particle that you created in your computer. You spin them around, twirl them around, and you basically, it's like making how do you, like making a bracelet, right? You got to tie these rope
Mhm.
one over another. Yeah. And at the end of the
Yeah.
day, you collapse them, you combine all the particles, you clean up the system, and you count. Hey, how many times did I braid A, B, C, D, E? And that allows you to do computation. You see, but that measurement is sort of like it's digital, basically.
Mhm. So, kind of the way I'm thinking about this as you're explaining it is essentially this new way of doing this anionic computing or Majorana mode, as it's called, allows you to reliably like essentially just figure out a reliability of counting, like how many times you've gone around. And when you have the ability to count things, it means then you can compute because computation is purely based on the ability to count or different ways of counting. Is that a fair statement?
Yeah, exactly. And this is like and that's why this is fundamentally different. Like you're counting discrete things. Like maybe a
Hmm.
good better analogy is like, for example, you can count the number of electrons in a material,
Hmm.
right? Like that is a discrete number. Like even though it's true that in quantum physics nothing is totally certain, but there are some discrete numbers that are pretty damn reliable if you
Hmm.
try to count them. So it's kind of like that. You're counting the number of particles or the number of knots or whatever kinks in your system, and that's why it's powerful. You're extracting extracting the good bits of the computation. You're trying to get, you know, you're trying to get integrity and like um, fidelity out of a system that might not be very noise prone, and
Hmm.
that's why this is like the holy grail kind of theoretically for quantum
Hmm.
computing.
Yeah, and I want to touch upon so as you know, as we've mentioned many times in this episode, and we had a whole previous episode about this as Mikey was asking the audience to tune into it about Microsoft's announcement. My question to you is how what would it take for you, Tim, to be convinced that somebody has achieved this lofty like ideal of the ultimate quantum computer? Like what would you need to see for that to happen?
Yeah, so of course it's like so let me just put this straight. No one has ever demonstrated for real that they have created some of these anion for like with definitive evidence that they've been created. And part of the reason it's so hard is because there isn't really a good way to show definitively that these exist. And the
Mhm.
reason is this. Um, the reason is in order for you to create these particles, your material has to be engineered very precisely, and it has to
Mhm.
have a what do we call we have to mix many different types of particles together in a material to create these exotic structures. To not go into the details, one thing you need to mix is you have to mix uh, electron and hole together. And what do people mean by hole is it's an absence of electron. Somehow you need to make the system behave the same if it have an extra electron or a deficit of an electron, which is very hard, right? And also you have to mix that in with what we call these magnetic fluxes, these vortices. So you have to combine multiple things together, bound them together into one object to create these anions. And then because they have such exotic properties, it's not crazy to think that you need everything to come in a Goldilocks zone, right? And because of that, these particles also need to be what we call gapless. They have to be zero mode. It means that it takes me very little energy to create one of these. And because of that, when I try to measure it, like how do I know I've created one of these? Yeah. The way to do it the way to do it is to see, hey, if I run a little bit of if I put my system in a little bit, plug it into the socket, right? Put a little voltage between them to see if there's some superconducting stuff going on. To see if a current flow without resistance, right? But as you can imagine, because it's a very quiet environment, like a little bit of noise a little bit of imperfection in the system could fake the signature, right? Maybe it just happened that there's a little bit of noise that if you add a little bit of energy, current would just flow or fake the signature because it's so precarious, basically. Therefore, even if you sort of measure this, even you find some kind of zero mode that's superconducting, it's not 100% definitive yet, right? There's still a debate,
Wait, isn't this already there? Like superconductors? Like, I mean, isn't that the definition of superconducting? What's the difference here?
Yeah. So the difference is that so the anyons is not just superconductors, It's more than that. It's the fact that they have to braid, So just having a zero mode at very low energy, that's superconducting. That's not enough yet. So, but that's one of the signatures. So I guess I would say that in order for you to discover one, but let me backtrack. Yeah, you're right that superconducting devices are plentiful, but these materials are generally non-superconducting in the bulk. Basically, they are not superconducting, but the boundaries are superconducting, at least theoretically. So you have to be able to see that in an experiment, and that's number one. And even seeing that it's not enough yet, how do you know that they can do this magic trick where you can spin them around and they'll make knots, right? So I would say yeah, it's not easy, but even just this basic signature of having a zero mode on the boundary that's superconducting in a non-superconducting material otherwise, that has not been done yet, basically.
So I want to talk a little bit about this gapless or zero gap, or I mean, you also mentioned zero mode. I'm just wondering, are all those related? And then what can you give an analogy for gapless or for this, like what does that even mean? Like, yeah.
Like this is kind of an important distinction between something that's gapped and that's gapless, right? So when something is gapped, it means that there's a threshold. There's a threshold you have to go over in order to do something. Like for example, like I don't know, like imagine I get up in the morning and go for a run, generally I would say that there's a gap, because like I wake up, man, I'm tired, like I need some energy. I can't just go for a run right away, But let's say you're really athletic, or I don't know, you're really well trained, you can just like get up in the morning and just go for a run. You don't need breakfast or anything, right? That's kind of like gapless, like it's like, or like you want to go to the grocery store, you go to the car, you start your engine, it takes you some gas just to start the car, Like a gapless mode would be kind of like, oh, if you want to go 5 feet, you don't need to start the car. The car can just spend a little bit of energy, just move like a mile, So you can just get it, yeah. And this is super important because theoretically, Majorana modes are predicted to exist only if you have a gapless mode for a variety of theoretical reasons. But intuitively you can understand this. Like, imagine in a material, in order for me to create these particles, I need to inject some energy in it. Chances are the energy will destroy the material because a lot of them have to be like super cold and whatever. They're really like they're really precious, right? Like if every time I make an anion, I have to throw so much energy in it, well, then that's bad. I could just destroy the whole thing, right? But the fact that these are gapless mean that I can just get just enough energy, just a tiny little bit, just to get it going. I don't have to pay that price for the, I don't have to pay the breakfast, for the computer to go for a run. And that's important.
That makes a lot of sense. Yeah, I guess but even if you had like a little bit of a gap, maybe not like truly gapless, but just just like a smidge of a gap, is that fine, or is
Yeah,
that
yeah.
like
I mean,
even that can destroy the material?
well, technically, in practice, nothing is truly gapless, right? When people say gapless, they usually mean exponentially small, very, very, very small. So it's so small that your material is not going to get destroyed. You can just add a smidget of energy,
Yeah.
so that's enough. So it's not totally gapless, but like close enough. So theoretically, you just say it's close enough to be gapless.
Makes sense. Makes sense. And so you have this gapless thing, and and what you're saying is that it'd be still hard to tell, even if you like. Is the challenge like determining, I guess, a gapless material that you can quote unquote braid, or what I'm trying to understand, like what is the challenge
Yeah, look.
in terms of convincing you that hey, I come to you and say, hey Tim, I have this beautiful quantum computer, it's gapless, it can braid my hair too, even though I don't have much hair, but it can braid my hair, what yeah,
I think part of
what say you?
I think part of it is just that people don't understand these materials that well. I mean, theoretically, they have a model, right? But what is the practical implementation? So I would say the burden is on the person making the claim. Like, you need to make a damn well convincing argument to the rest of the community that you've actually created one of these anions and successfully braided it. I think the bar, unfortunately, is lie on the people who are claiming it. And
Can
yeah.
you, oh, I was thinking, can you tell me, like, again, maybe give an analogy for like what braiding means? Is it like my ability to manipulate particles and like move them around in this 2D, like physically, or what is actually braiding?
Yeah, actually, in some of these implementation, they are literally braiding, moving the particle around. So what they do is, I
Oh,
mean, I did some research in this. So they have this material, and you can create anions in. Let's say I have a hunk of material. You can create
okay.
anions in 4 places. Like a diamond shape, right? When they braid, they are literally they literally create a little shuttle. Basically, they can put some electric voltage around some of the region to trap them, so they can heat up the material a little bit to make them non-superconducting, but then the middle of the particle is superconducting, and just shuttle them. So they're literally shuttling them around and spin them around one another. They're literally braiding them like your hair, basically. Although imaginary
Oh.
hair in this instance. They're literally moving them around, shuttling them around physically. Yeah. And
Yeah.
then they measure it. So the idea is that once you move them around, the system changes. So Microsoft they wrote a paper and they claim that they can measure what comes out. So I guess the definitive proof would be that you have this system with a few anions that you believe are anions, move them around a little bit, move them around a few more times, and then measure it to see that the measurement actually come out different. And that will be the crux, to really just show it.
Got it, got it. And we're essentially almost at time. And so one of the questions I got from a lot of people after this episode aired was, if what we're saying, and at the end of the last episode, was that what Microsoft was saying wasn't like the full thing. They didn't actually like create this this chip they have is, it's unclear whether it works or not. So what did the Microsoft paper actually do in that case? Like, what did they do and what didn't they do?
Yeah, yeah. I mean, you read the Nature paper, it's very, very disappointing. And that's why, like I said before,
Mm,
even the editor from Nature put on a disclaimer because they showed no evidence. The paper didn't even mention, they show no evidence that such anion exists. So you don't even know if the chip works. They basically said that they created a device that if the anions existed, they could measure it, basically. That, and
oh,
so
so it's just yeah, go ahead.
yeah, so it's a kind of a strange paper, right? Like, because you don't have anions yet, so how can you prove definitively that it works? But they're showing that, well, if it did exist by simulation, calculation, some measurement, that these devices should work, basically.
Ah, okay, okay. So, oh, I see. But I guess the proof is in the pudding that the only way to know that it truly works is if there were anions.
Yeah, I think so. I think you need the
Mm,
experimental proof, and it's still absent. And like honestly, this could be a Nobel Prize winning experimental
mm.
result. So why the hell did they not put out a paper if they found it? We're all waiting, I think.
Yeah, that's totally fair. Yeah, so in our tradition towards the ends of our episodes, is there any words of wisdom that anions, braiding, and quantum computing have taught you?
Um, I mean, the past few days I've spent a lot of time looking at some lecture notes. So you know, condensed matter physics is not my cup of tea. It's not an expert in it, but it is tangentially related to particle physics. So I do take an interest, and it is interesting to me that the anionic computing and topological quantum computer. It is such an interesting development because for whatever reason, accidental or not, it actually merges. Like it's almost feels like a miracle, right? Like people had these materials, and then they well, let me put it this way, um, and then people come up with these theories of anions, which people thought had nothing to do with reality. These are just imaginary worlds. Whatever. Who cares? We don't live in a three-dimensional world. But lo and behold, people start finding evidence that maybe these theories can be realized in materials, at least approximately. Yeah. And it just feels like one of those instances where physics really is discovered, not invented. Like who would have thought, right? And it tells you that we got to be doing something right here. I feel like, like how could it be possible? I think there's some like interview with like Frank Wilczek or whatever, like or Chern Simons, whatever. Like back in the days, it's just completely a theoretical curiosity, right? Like it's like what the hell? Like who would have thought? Then it makes you wonder, like looking forward in time in the future. Like a lot of people say, oh, theoretical physics, who cares? The Higgs boson, whatever. It doesn't impact humanity, right? In any way. But, think again. Maybe we won't see it in our lifetime, but like 1,000 years, I don't know, 10,000 years later, we could be looking back and be like, hey, look, guess what? These crazy particle physics, I don't know, 10 dimension, 11 dimension thing. Hey, maybe they're right there all along, one way or another, in some materials,
Mm.
in some simulated universes, whatever. And that's just super interesting to me, I think. And I think that speaks to us, that's one of the reasons why we should study physics, not because of some immediate economic value, but that's just, it's something that's calling to us, I would say.
Hmm. Well said. Well said. I want to end this episode by giving you a challenge question. In one word, can you state what the Amazon quantum computing chip that made an announcement? What would you say in one word to describe it?
Oh, I briefly read it. I think they are trying to chase the hype, but what they did not seem that impressive to me. I think it's less impressive than Google's Willow announcement. It's just some error correction thing, and the error was still like the fidelity is like 99% or something, and that's like terrible, basically, right? Like you need like something like 1 in a million or something to get real work done. So I mean, I don't blame them, right? Like they with all these announcements coming up, I don't know, their stock price coming down, they need something. So sure, publish the paper.
I was looking for the answer nothing burger, but maybe that's 2 words. But anyway, yeah. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you all. Bye bye.